So let's move to the first discussion of week 2. And let me make a few remarks since I know that some people are joining for the first time for week 2. And so I want to remind a little bit how these discussions work. So these discussions are something new. We are trying, so we are tweaking as the days go, and we are hopefully improving a little bit. And so let me mention not only how it has been working so far, but a few things that we hope will improve by an epsilon more for this week 2. So the idea of these discussions is, first of all, to keep to try to generate a more informal feel for the meeting and for us to have fun chatting with each other and seeing each other. So please, if you are participating in the discussion and if you can keep your camera on, that helps give this informal feel to the meeting. Now, let me make 2 comments then. Let me describe the 2 parts of these discussions. The first part is where the chairman introduce the topic that is going to be discussed, where the leaders of this discussion remind us a little bit about what we are about to discuss, present some open problems, etc. So this period of 20 minutes, it's in this case totally up to Sergey and Igor to distribute and do absolutely as they please, eventually invite people to speak, whatever. It's 20 minutes totally up to them. Now, there's something that we realized, and by the way, this I should also thank the advisory committee for many useful feedback during this weekend, that one thing that could be very helpful, especially for non-experts, is to get the PDFs beforehand, especially for this type of session where we are thinking about problems and thinking about questions to ask. So I urge everyone to please send me their PDFs of your discussion sessions ahead of time. And as you notice, this discussion session slides are already online on the next one, and we will soon post the next one. So that should hopefully help a little bit. The last 30 minutes are the period for the audience and for everyone to discuss, make comments, ask questions to the leaders, ask questions to each other. And for that period, please raise your hand, wave, and we will, in this second week, I will really try to give priority to people that did not speak yet. So please, I encourage you very strongly to try to participate if you did not in the first week. If you did not participate yet, and if you wave, then you get really ultra top priorities. So please, I encourage you to participate. But if you are really, really shy and you really don't want to raise your hand, then you can use Slack. I encourage you in that case to use Slack and post your questions there beforehand, and I will transmit them to the discussion people. So don't forget that often the most basic questions and the most down-to-earth questions are the most relevant ones, and the very latest development on the latest supersymmetric generalization of this or that will probably fade away in a month or 2, whereas some big questions about large NQCD will definitely survive for a few more years. So don't be shy and don't be afraid of asking what would be called normally basic questions. So I guess that's it. This was a slightly longer introduction. And the other thing I should say is that, as you notice, the discussions are right before the coffee breaks or at the very end of the day, because while I will try to be rigorous as much as possible with the first 20 minutes, I will not be very rigorous with the last 30. So the last 30, if they go a bit over time, that's fine. People can just leave and go for coffee. As soon as I see cameras on and people are having fun, I will keep the discussion going. So again, if you are participating and if your internet allows, please turn on your camera. And I pass the floor to Sergey and Igor, and I'll start counting the 20 minutes. Thank you.
Okay, thank you very much, Pedro. And I want to start by thanking all the organizers of this magnificent worldwide virtual event. So I've been entrusted with making a few remarks on color confinement. Just one second. Yeah, this picture is both to remind us that it is organized in Brazil and about the beautiful homepage of the conference, and also of the fact that most of the things I'll be saying will be a repeat of what you hear all the time. But hopefully there will be something new, and in particular, Offer's great review talk this morning has a lot of overlap with what I have to say, but let me just start with why work on the confinement problem. It's a kind of classic problem that comes to us from the past. It's one of the problems that has cache values associated with it. It's one of the clay millennium problems. And you can see the formulation, brief formulation. You can also find a much more elaborate formulation online, and the status is unsolved, so there is still work to do. Then going back 21 years to an interesting event at another great string conference, Michigan 2000, Millennium Madness. There was a call to submit problems for the next millennium, and I and Oyvind Tafjord submitted this very basic question: can one quantitatively understand quark and gluon confinement in QCD? It came in dead last in these top 10. You can actually still find this online on John Preskill's Caltech homepage and see that basically none of the problems have been solved, at least completely. I mean, some may be addressed more than others, but this problem perhaps should increase a little bit in relevance in view of recent developments. In particular, there is a flourishing of experimental results on strong interactions and discovering of new states, tetraquarks and whatnot. So just a few words about the basic confinement problem, lattice SUN gauge theory. Probably all of you know this. There is the plaquette action, and the basic criterion is whether the Wilson loop has area law. If it does, e to the minus something times a, then the quark anti-quark potential is linear at long distances, and we have confinement. It's very easy to prove this in the strong coupling expansion, where you just tile the big loop with lots of small loops, and you immediately see the area law. But of course, it's harder than that because of asymptotic freedom. We really have to go from strong coupling to weak coupling at the lattice scale. And then things are much harder to see analytically what to do. In principle, confinement can disappear in this limit, but numerical simulations decisively tell us that this is not the case. And while maybe in the 70s you could criticize them because the lattices were small, now they've grown to 100 sites per dimension and perhaps can even go further. So the computers have not been standing still for sure, and we have constantly improving data. Okay, so now what we see, this is one of the commonly shown pictures from Lineweber's group from the lattice. You have probe quark and anti-quark, and we show action density between them. You see that it's collimated into a fabled flux tube or QCD string. It's not infinitely thin. It has thickness of order 1 Fermi. And while the potential between quark and anti-quark is approximately coulombic at scale below 1 Fermi, it kind of becomes linear at scales above 1 Fermi. So strings have definitely been observed in numerical simulations of Yang-Mills theory. They're a very real thing. And they're governed by non-Bugota area action, as you heard from Ofer's talk, and we'll soon hear from Sergei's remarks, with corrections. And it's more than the lattice. Even in nature, we have evidence for these flux tubes because high spin mesons are described by these spinning open strings. They have energy density, again, characteristic scale about 1 GeV per Fermi, which is a lot of energy. If we could harness it, would be great, but we can't because n is too small. What happens? So while we see the evidence that that the leading Regge trajectories are linear, the states become too broad to identify for spin around 6 or something like that and above. So this is a very basic Regge trajectory for rho, A2, and so on. So this is still one of the best empirical evidences for relevance of string theory to real world. Now, of course, large n helps. I always tell people if n were not 3 by 33, there would be no mistake that we're seeing these Regge trajectories would continue to much higher spin before strings can snap by QQ bar creation. As we heard many times in large N gauge theory, in the string dual to large N gauge theory, this coupling is 1/n. And in particular, this is an example of a stable non-supersymmetric theory of closed strings, loopholes, and open strings, mesons. Of course, as we all know, adding maximal supersymmetry makes this theory conformal, and then we basically know the dual of the theory type 2B string in ADS 5 crosses 5. In this case, of course, there is no color confinement, but the surprise of 1998 is that there are still strings. And furthermore, it is possible to find more general backgrounds that do describe confining theories. So let's just go back to the now classic ADS CFT result of how you compute the QQ bar potential. You connect it by a string, the fundamental string that goes into the 5th dimension. And because of the scaling symmetry of the whole story, you do see Coulombic potential even at strong coupling, where this dual gravity is applicable. But then if you introduce phenomenologically some kind of infrared wall, then the string will go and lie down along this wall, and there it becomes really the confining string. So it happens generally in warped metrics, and there has been a lot of model building, a lot of these along these lines. Right. The important thing is that the warp factor doesn't vanish at this infrared wall, and then you've got yourself a confining string. Now, just a few words about this warp throat example that has been mentioned at the conference, mainly in the setting of phenomenology and cosmology. But originally, Stressler and I were really worried about it in the context of confinement and chiral symmetry breaking. It's a kind of toy top-down example where you have a rather very well-defined weakly curved solution, which is a warp product of deformed conifold and R3, 1. And the warp factor exactly has the properties that were shown before. So one can actually use the technique to compute the string tension, and nicely it incorporates from the nearly Coulombic behavior at short distances to linear behavior at long distances, just like in QCD. This is, I'm showing the latest data actually from long ago. So this example incorporates dimensional transmutation where the argument of the log becomes the QCD scale. With maybe bold interpretation, you could say that gauge gravity duality has provided us with a kind of physicist proof of confinement in some exotic gauge theories, perhaps even more exotic than the parrot on my first slide. But we don't really have the dual of QCD because of the asymptotic freedom. The asymptotic freedom makes the gravity dual description difficult at short distances. So if you want the full flow from UV to IR, we haven't come up with it in spite of efforts, mainly 20 years ago. So maybe it's time to come back. But one can also go even further back in time, and as a modest step, drop back to some 1+1 dimensional gauge theories, which can also provide some intuition. Of course, there is the famous Hooft model, which is exactly solvable in the large N limit, just 2-dimensional QCD with fundamental quarks at large N. But that doesn't have any adjoint degrees of freedom like gluons. So, so let me mention this adding adjoint matter. Then it becomes not exactly solvable, but can still be, it's a kind of useful toy model for practicing your light cone wave functions. And this was attempted going back to the early 90s. And in particular, the model with an adjoint Majorana fermion, which is a toy gluino, has been receiving some modest renewed attention. It is super normalizable, has non-trivial set of vacua, and actually a mass gap even at the limit of M going to 0. The mass is not renormalized. And interestingly, just to comment on something that's been said, it has both Fermi, so it has both bosonic and fermionic kind of blue ball type states. And asymptotically, they do exhibit degeneracy for a special value of mass, as pointed out by Kutasov. in 93, it exhibits actually exact Bose-Fermi degeneracy. So now the new result, there have been very interesting new results by Kamargotsky et al. And let me mention a paper that we wrote with Silvio Pufu, and who is at Princeton, and Ross Dempsey, a graduate student at Princeton, where we basically, in addition to the massless adjoint or light adjoint, we added NF fundamental Dirac fermions. So it's a kind of souped up version of the 't Hooft model with additional explicit adjoint quanta. Now there are much more complicated states where mesons have a Q bar and Q with a bunch of adjoints in between. And they can again be either bosonic or fermionic. You see multiple Regge trajectories. And the interesting thing here is that this theory actually, when this adjoint mass is zero, it's not confining, contrary to the sort of intuition you might have that all 1+1 dimensional gauge theories are confining because just perturbatively the potential is linear. Basically, what happens based on the results that we observe with Dempsey and Pufu is that the spectrum of mesons is continuous above a certain threshold, which means that the QQ bar potential is asymptotically flattens out. At short distances, it's linear, but it just flattens out. And this means that the massless adjoints renormalize string tension to zero. This was sort of conjectured long ago, and then using non-invertible topological lines was demonstrated in a different way by Kamargotsky and collaborators. For a very small mass, it becomes non-zero, giving a model of weak confinement, and one can study various string tensions in this model and so forth. So let me summarize and pass on to Sergey. One lesson is don't take confinement for granted, even in 1+1 dimensions where it just seems obvious. It can actually be kind of screened in a certain way. I think proof of color confinement in 2+1 and 3+1 dimensions would be very important, not both as basically giving us confidence that we're doing the right thing, and also for practical reasons. What we would like to improve connections between QCD and fundamental strings, and hope to get new analytical insights and approximations to spectra of hadrons and K-string tensions, where K is the number of quarks on one end and quarks on the other end. And this should be guided by the improving numerical results on SUN gauge theories for a range of N. Recently, there was yet another big opus by Thanadora and Tapper, and there are other groups working on this. So I think good road lies ahead, I think. And let me finish here and pass on to.
So while Sergey sets up his share screen, let's thank Igor. So you are at 14 minutes, more or less. Of course, I'll give you a little bit more. You might be muted if you are speaking. We can see your screen, but I cannot hear you. Can people hear? Okay. No. Maybe if you disconnect your headphones, it might work. Sometimes that's the issue. So just.
Is it better now?
It's working.
Yeah, I don't know what happened with my headphones somehow. Okay, so sorry for this confusion. So let me present my remarks, and I hope we'll have a fun discussion session afterwards. And my remarks will be roughly, well, they will be largely complementary to what Igor covered. So namely, I will assume confinement. And the main question I want to discuss is what is the resulting string theory one gets there. And I think compared to some other sessions, one of the questions to discuss here is it feels that relatively few people are actually thinking about this problem, and it would be nice to discuss why is it so. And I think the related question is what are the right questions to ask in this field. As far as the first question is concerned, oops, sorry, it's not, yeah, okay. The answers I heard is that, well, gravity is cool, QCD is boring, there is no clear, sharply formulated problem here, the problem is too hard, the problem is morally solved by holography, and clearly there is some tension between these answers. And I will try to convince you in the few minutes which I have that actually all of these misconceptions. So first, let me start with a limited sharp version of the problem, which was already explained by Ofer very nicely in much detail. Namely, let's consider an infinitely long string in the string planar limit on the gauge theory. It defines a microscopic relativistic theory of fluctuating 2D geometry, which I'll naturally to call asymptotically flat 2D gravity. And in this setup, then the natural question to ask is what is the S matrix of this object? As reviewed by Ofer, the low energy asymptotics is largely fixed by symmetries. This is a system of Goldstone bosons plus maybe some additional massive modes. So I think as in many theories of gravity, the most interesting question to ask what happens at high energies here. And well, that one advantage of having sharp formulation of the problem is that at least it allows to see what are not good questions to ask. Namely, I guess in early days of like idea of 1/n expansion, the reasonable goal seemed that, well, 1/n expansion looks like a genus expansion. So the reasonable goal was to solve the free planar theory and then to develop string perturbation theory. And that works beautifully in unequal force or Mills. And this picture tells us that will never work. It will never really work in pure glue. And the reason for that is that Walsh-Sheet theory, which you obtain even in a strict planar limit, it's still non-integrable. There are, as explained by Ofer, there is particle production on the Walsh-Sheet. So we won't ever be able to really solve the planar limit of this theory. So the question, what can we do instead? Well, and there are several directions which I see. First, it would be interesting to find a confining theory with integrable dynamics on the Walsh-Sheet. It looks very hard, and I will comment that maybe there is a reason why it's impossible at dimensions higher than 4, higher than 2, sorry. But I think the best place to look may be the family of two-dimensional adjoint QCD-like theories, where there is a chance for that. Then one can do bootstrap. And finally, one may try to develop high-energy perturbative expansion for the Walsh-Sheet theory. So let me give some comments on this last point. Well, and it kind of addresses what Ofer was asking in his talk. So why would one expect that there is something like integrability at high energies on QCD string? And I think the cartoon which motivates that is presented here. This is a cartoon of scattering, of Walsh-Sheet scattering at high energies in the asymptotically free theory. So degrees of freedom on asymptotically free theory at high energies, they should be partons, gluons, and pure Yang-Mills. Then scattering goes through hard collision described by perturbative QCD, but because series asymptotically free, one doesn't expect particle production there. And then because string cannot break, will be this zigzag period, and then particles will bounce back. So first, this picture tells that the full S matrix will be factorized. There will be long energy long distance contribution coming from zigzag and UV contribution coming from hard collision. And because zigzag produces non-trivial time delay, it tells that the theory cannot be free. The best it can do, it can be integrable. So that's a kind of motivation of thinking about high energy integrability. And clearly, well, it's interesting to study this zigzag. And it can be studied quantitatively, at least in 2D adjoint QCD, where actually it does lead to interesting n-body relativistic integrable model. And there are two consequences of the zigzag. One is that it leads to long time delays as a result of collision, reminiscent of TT bar deformation. But it's different for TT bar because if the two particles are different, two quarks are different, then actually this process here goes, it's total reflection rather than total transmission in TT bar. Still, it's kind of similar in spirit in many respects. And furthermore, if there are light degrees of freedom here, like in high dimensional Yang-Mills, then it's expected, because there is long period when particles move with acceleration, one expects that there should be copious soft particle production. And that's maybe kind of a sketch of the no-go for exact integrability in confining theories in high dimensions. But also it tells us that TT bar is described by some very simple model of quantum gravity. It's roughly speaking JT flat space, JT gravity. But it tells us that the 2D gravity describing actual confining strings is more interesting. It also has this property of soft particle production, which is we all like in conventional gravity. And also this picture suggests what the expected degrees of freedom. So basically one inserts bulk fields into Wilson lines, and in 4 dimensions, this way one gets Goldstone modes, but also one expects to get gluon paralyzed in transverse plane, which corresponds to kind of pseudoscalar excitation on the voltsheet. And that's exactly what one finds on the lattice. And that's what we call axion. We should probably call it just gluon. And interestingly, as was mentioned by Ofer, so the coupling of this particle on the lattice takes an integrable value, supporting this picture, which was presented before, that maybe there is some approximate integrability in high energies. So let me come to Bootstrap. So Bootstrap, as we heard already in some talk, so it allows to restrict high energy, some Wilson coefficients in the low energy theory. And the interesting conclusion which one finds here, one finds that there is a boundary of allowed region, and there are 2 shores of this boundary, and one shore can be described by something like roughly conventional holographic Liouville shore, because what one finds there, one finds a sharp scalar resonance on the voltsheet there. And another shore, which corresponds to more like actual QCD, there one finds sharp pseudoscalar resonance. And there is a piece of good news here that one really finds 2 shores rather than an island, meaning one can interpolate from one to another. So it looks like that these 2 regimes are not completely disconnected, but also it suggests that, well, actually, actual QCD string, it operates in different regime than conventional non-critical strings or holographic models. So finally, she already asked this question. So what is it? Can we say anything about short strings or glue balls? And at Strings of Jerusalem, I presented predictions, semi-classical predictions for glue balls, quantum numbers of glue balls in D equals 3 on Mills, well, which predicts the quantum numbers. And that was an experimental situation back then. It worked for first 3 levels, and there were some tensions at the 3rd level. And this is experimental situation now. It looks to work very nicely for first 4 levels, which means first lightest 39 states. So I think this picture really shows that glue balls, they do look like oscillating strings. And we structurally understand, I think we're close to claim that we structurally understand the whole spectrum of glue balls in D equals 3, which I think is very interesting. Of course, there are many details here about mass splittings, which needs to be calculated. So let me finish with a propaganda slide. So one can often hear, well, that string theory may be beautiful, but we may never know whether strings are realized in nature. Well, I think we see that's clearly wrong. QCD is a theory of strings, and string theory was born to describe strong interactions, but then was repurposed as a theory of gravity. But I think one of the lessons we learned in the last 20 years that gauge theories and gravitational theories, they are much more close to each other than one could have expected. And in some sense, confining strings, perhaps they provide the most basic example and reason for connection between gauge theories and fluctuating geometry. And they may be the closest we'll get ever to doing experimental quantum gravity. And I should say that, well, in particle physics, we may wait another 30 years for a new collider to come and provide new data for us. But I think we are very lucky. So we have a tractable and fundamental problem to solve while waiting. And I think participants of String 2051 will be happy and puzzled if we don't make an effort and solve this problem now and leave it to them. So thank you.
Thanks very much. Let's thank Sergey and Igor. And as I said, please, if you can turn on your cameras, raise your hand if you want to ask a question, wave if your question is related to what is being discussed at the moment. And maybe there is already a question in the chat that from Nikolai. Nikolai, maybe since you would be one that I don't think you unmuted yourself yet. So I'll put you on the spotlight if you are there.
Yes. Hi, everyone. Yeah, well, I asked my question and also I followed up, so I don't have much more to say. I was asking whether, well, n equals 1 star is an example that is a 4D gauge theory. Well, obviously a toy model with a certain amount of supersymmetry that has confining vacua. And so I was wondering whether it fits the bill as an asymptotically free theory or not, because of course the UV is n equals 4 Yang-Mills, which is, well, it's a bit weird. It's both asymptotically free and asymptotically safe. So I'm not sure if it's a useful toy model that we can learn stuff for real QCD, but anyway, so I was just asking for an opinion from Igor, basically.
I mean, I can elaborate on my comment a little bit. I mean, of course, embedding theories in n equal 4 super Yang-Mills is fine, and we can make some of the superfields massive, and then formally you get just pure supersymmetric law dynamics. That's great. But I think we want to be in the regime where first you decouple all the extra degrees of freedom of n equal 4, and then you follow the RG of the supersymmetric law dynamics starting from pretty weak coupling. So you start, that's what I feel. So you have to get an approximately asymptotically free regime, and then you have to see the dimensional transmutation in that theory to declare victory. And there is a related story. So generally, I think one thing that you said is very valuable, that maybe as a good goal, we should not be thinking about the just pure glue SUN, but supersymmetric SUN, n equal 1 supersymmetric, because that's a confining theory with lots of wonderful properties. Another approach is this deformed conifold that I mentioned. There again, formally, far in the infrared, you just have pure supersymmetric law dynamics. But the problem is you want to be in the regime where these cascade steps are very far apart. So you have to, again, exit the gravity regime, you know. But I think there is some glimmer of hope here that maybe if you go to sort of start with this, as often in life, you're sort of on the other end of where you want to be, right? Like we saw that in strong coupling expansion, you're far from where you want to be. I think in gravity duals, you are also kind of far from where you want to be, but hopefully we can make this journey. Was that a reasonable answer?
Yeah, I was just wondering out loud. Yeah, certainly. But we know models of like pure n equals 1 Yang-Mills, like Marcena Nunez, but then the UV completion is
not
a bit
pure n equal 1 Yang-Mills. It has lots of other stuff.
Right. The
It's
KK scale
scales.
is not.
We want to decouple.
Exactly.
We want to separate scales so that we can say for a very large range of RG flow,
exactly,
we're in the n equal 1. I mean, as far as I can tell, all the models we know have this issue, and that's why I could not declare victory by gauge gravity duality. And
maybe a final comment, maybe this scale that we want to split is, again, related somehow to this issue of last week of ADS4 scale separation. I mean, it seems that we're unable to kind of find this hierarchy of scales in supergravity so that we keep control.
Right. I think it's inevitable we have to exit the supergravity limit. That seems clear, and that's why we need a whole new toolbox.
Jaume?
I mean, my comment is unrelated to ADS50, maybe I don't know if people wanted to comment about it.
No, but people are not waving. No, this is a very clear rule. If you are waving, that's okay. Otherwise, it's new people that have priority.
I just want to make a comment about the presentation by Igor and Sergey, and it's just about what are the expectations about confinement versus deconfinement. And I think kind of recent work not in 2 dimensions, but in 3 dimensions actually kind of shows that actually 3-dimensional gauge theory, say with an adjoint quark, actually, contrary to naive expectations that it would be a confining theory, it's actually deconfining. So I think we have to upgrade our expectations about what happens to confinement, even in 3 dimensions. And one important difference in 3 dimensions versus 2 dimensions is that in 2 dimensions, the confinement essentially disappears the minute you give a tiny mass to the quarks. While this is not what is expected in 3 dimensions. The confinement is expected to survive kind of a finite mass for the quarks. So that just was a comment.
Could I make a comment, just a very brief comment to respond to this? I think in 4 dimensions, it's also true. If you add enough enough, say, gluinos, adjoint fermions, you will just lose asymptotic freedom. You will go to the infrared free theory, right? So in any theory, if you add enough adjoint, in any dimension, if you add enough adjoints, you lose confinement, it appears.
No, but I was talking just like exactly the example you were discussing, 2 dimensions, just add one adjoint. Like, as you went
right.
with one.
Yeah, where the boundary is for in 3 dimensions with enough adjoints, you very clearly see that if you take the large NF, like many adjoints, you very clearly see it's a conformal theory. Then you start dropping NF, and the question is, where does this conformal window end? That is the hard part. And yeah, I should learn more about your work about 3D, but I would say it's definitely always true that with enough adjoints, you get deconfining behavior, and where the boundary is maybe somewhat dimension dependent.
I don't think it's about the number of adjoints. It's just one Majorana adjoint.
Yeah, no, I was just bringing in the case of many adjoints, right? Where you clearly see the CFT in 2+1 dimensions, right? So then in 3+1, you also see a free CFT in the infrared.
But it's not the same mechanism that Jaume spoke. When you add lots of adjoints, the phases that you observe of gauge theory are the same phases that you see semi-classically.
Okay.
In the example that Jaume brought up, the deconfined phase is not semi-classical, it's extremely strongly coupled.
Yeah, no, I agree. So, sorry if this comment was a little off mark, but I've been thinking a bit about related things.
Not at all. Let's maybe, Rajesh also has not yet chimed in the discussion, so following the new rule, let's move to him.
Thanks, Pedro. So I just had a sort of a thought. I wanted the experts' opinion in trying to connect the top-down to these effective strings, whether, and this was something with Ofer we were just chatting also, but whether this anomaly term could be something which is very robust and which is something you could hope to connect between from the bottom-up approach to the top-down approach, and the term that Ofer mentioned in his review, the one with 26 minus d as its coefficient, and in particular, that seems to be it seems to be a very universal term, and it's not unreasonable that you can sort of see something like that in a microscopic description. And in fact, in the ADS3 example, we see something very close to that sort of a term. So I was just wondering whether anyone had any thoughts on the possibility of connecting these two approaches through a term like that.
I may say that. Well, first of all, this term is really just as Ofer explained. This is really calculable one loop effect in low energy theory, and this is the same effect as familiar Versor anomaly. So in that sense, it's present everywhere. But I think, well, at least from my viewpoint, there is interest in numerology, which is somewhat related to what you are saying. There is interest in numerology related to this term. Namely, one thinks about 4-dimensional gauge theory, that the coefficient which appears in this term, it's exactly the same coefficient as in one loop beta function. It's like 26, it's 26 minus 4 is equal to 22.
22, yeah.
Which is, and one loop beta function clearly very, very UV thing. And I think it's not a coincidence. For instance, one may add adjoint matter in gauge theory, add adjoint scalars and fermions, and one knows then how this thing is shifted in UV theory. And it's shifted in the IR theory in the same way. And that's kind of, I think that might be one reason why integrability, what I'm saying, that integrability is in conflict with confinement. So somehow to cancel this term, that means to restore integrability, in UV theory seems to correspond to getting conformal theory. But of course, it's a mystery how to relate it to, which might be related to what you're saying, because it requires really relating IR and UV to phenomena.
Yeah, in fact, that's interesting that you mentioned that, because the picture I was having from the examples I'm familiar with was that term is essentially coming from the radial mode, from the radial direction in a holographic picture. In some way, it probably could be thought of as the kinetic term of the Liouville mode, or the radial mode, and that would be natural that it should have the information about the beta function. So yeah, okay, thanks.
So as I see no new people, maybe let's go to Sandeep, and then unless a new people raises his hand.
I'll quickly ask and get off so others can participate more. But I wanted to respond to Sergey as to why more people are not working on the QCD string by just saying why I'm not, so you can respond to me. You know, I was always held back because the real world has light quarks and therefore strings will break. But I say this by adding all so that, you know, when you go to, you know, talks on data and phenomenology, which I used to, at least till some time ago, it's a striking fact that the process of fragmentation, right, how quarks break up into hadrons is actually often modeled using a string model, like the Lund string model and so on. And so, you know, in the real world of phenomenology and using models, the string model is quite useful for that process, which involves strings breaking due to quarks. So am I being too conservative? Is there a way to put that on a better analytical footing and make it actually useful? This was my question. You can ignore it, all of you, if you like.
I think it's a very good point. But also, well, first, as you mentioned, like really in the real phenomenology, people use string model. But also, we know that one-on-one expansion then for many purposes works quite well. So it seems reasonable. And one-on-one expansion at leading order, the string breaking effect is suppressed. So it seems reasonable if one wants some project systematically, it seems reasonable to start at infinite end limit where string breaking doesn't happen and then include that perturbatively.
But just very quickly, I mean, would it be worth trying to actually model fragmentation in a systematic 1/n expansion and seeing? I don't know of any work which has happened in that direction, but you can correct me.
I think that's absolutely yes, right? But we just don't understand well enough the QCD strings to do that.
Thank you.
I think Pythia and such programs use basically Nambu string, I thought. So in that sense, it is phenomenologically relevant. But yeah, maybe, I don't know, maybe they tweak the string action too to some extent.
Well, to add to this, yeah, because we see, like in pure glue, we see this massive excitation on the string world sheet. And there are reasons to expect that it will survive also in actual QCD. And if so, it should translate into some features maybe of the PDFs, really of some nature of physical observable. So I think that's a very interesting question, but it's just that one, at least for me, it's too hard.
Thank you.
Yeah, so I have two questions related to what Sergey was talking about. So first is, so Sergey, you were suggesting this approximate integral between the Heinrich limit on the confining string. I'm trying to understand how to formulate that kind of in the language of usually what like to think about RG flows. So does it mean that there's supposed to be a UV-CFT and we can think of some deformation of that? Or I mean, what does that actually mean?
Well, no, I think we know that there is no UV-CFT because of this TT bar like phase shift. So this integrability, if it's there, it's really it's some TT bar asymptotics. So it's asymptotics which is incompatible with CFT. And I think in massive theory, like adjoint QCD in 2 dimensions, I think there is a real chance, as I was trying to say, that there is a hope that really there will be actual integrability because there are no soft particles. In actual QCD, because there are soft gluons, I think it's hopeless to have, well, but I will be happy to be wrong, but it's very hard to expect actual integrability. But I think there is a hope to get integrability for some properly defined exclusive observables, like some jet-like observables. So in this scattering I was talking about, yeah, one expects there is lots of soft particle production, but as one always does in QCD, one may try to define some jet-like observables, but suited for these 2-dimensional kinematics. And I think there is a chance that behavior of those described by integrability, by some integrable approximation.
this TT bar phase you're talking about, you know that's true in the high energy limit, or is it the low energy expansion? Because
well, that's the picture which I draw, right? So I think, well, if one, and in two-dimensional adjoint QCD, one can really derive that. So because if you consider wall-sheet scattering of two partons on QCD string, yeah, they go through each other. That's asymptotic freedom, and they stretch the string. And there is a long period we describe really by semi-classics. And from that, you get time delay proportional to collision energy. And that's CT bar.
Okay, fine. But you know, you might be able to remove that gravitational dressing by going to a different gauge, just like the usual going between, you know, static gauge and the conformal gauge, right? I mean, yeah, one could imagine maybe in another gauge, you actually have a CFT in the UV.
Well, it's not a question of gauge, because this is a physical effect, which is this is time delay, but one can do TT bar undressing, and that one will get kind of that. So I think the expectation for S matrix, indeed, there is a hard process. Then there is some factorized, like some dressing, TT bar like dressing, which describes this long time delay. And that's what we mean by integrability. By the way, this integrable series, which Ofer was referring to, they're all just TT bar dressing of free series. So by integrability, one really means here just this TT bar deformation.
I see.
But what I also was trying to emphasize in my talk, that in actual QCD, like in 3 and 4 dimensions, one expects that on top of these two things, on top of this long time delay and hard process, there is also copious soft particle production during when this zigzag forms. Just because there is like ends of zigzags, they move with acceleration, and one expects Unruh type radiation coming from there. So that I think is very.
Let me maybe ask something related to that. So when we scatter these two particles, these two goldstones in the flux tube, the absolute value of that S matrix that quantifies the amount of particle production at high energy, do you think, or do people think it goes to 1 and it's purely elastic, to 0 and it's dominated by inelastic, or something in the middle?
You mean 2 to 2 S matrix, right?
Yeah.
My expectation, it will be exponentially small, just like 2 to 2 scattering in gravity. Well, because it is a theory of gravity. And the reason for that is because there is a semi-classical process, which one expects to be there in the presence of massless modes on a string. So the dominant process is really when you produce lots of stuff, plus maybe two hard jets. But a strictly 2 to 2 process, I expect that to be exponentially small.
Let me maybe pass to Zohar. Yeah.
It's about, I think one question that could be discussed is that this proposal of Sergey for the asymptotics of the scattering in terms of this TT bar deformation is also coincident with the classical analysis, classical answer for the time delay. And I think it's kind of interesting as a general physics fact, if it's correct, that the high energy limit is the same as the classical limit.
Well, but again, that's something familiar in gravitational theories, right? So that some like rough aspects of high energy scattering can be captured by semi-classics in gravitational theories. And I think that's one way to view it this, right?
Is there an expansion you can do to characterize the deformation away from this UV limit that's integrable?
Well, that's an excellent question, and well, I think the hope is that, well, it's some kind of high energy expansion, and the hope it may work exactly because that this violation of integrability is some long distance process. So kind of there is a hope to factorize it away. That's one strategy, and another. Well, again, of course, in massive adjoint QCD in 2 dimensions, there, if the mass is heavy, then there is an expansion parameter. But also one may try to do something like D-26 expansions. That's related to comments which we had before. Of course, D-26 for D equals 4 sounds like a big parameter, but it is divided by something like 16 pi or something. So one may try to do maybe formal expansion in that parameter, which would be like expanding around a conformal field theory in the UV. But yeah, maybe there are other smarter suggestions, but that's one of the central.
Maybe let's go to Mukund.
Thanks. I was just going to, I had a question, but let me pick up on something that was just said. So when you say that the theory is like gravity, you really mean in the TT bar sense that it's
well,
the world sheet.
Well, at the most basic level, I mean, this is a theory of fluctuating 2D geometry. And in TT bar case, we know exactly the corresponding gravitational theory, which is roughly speaking, flat space GT gravity, meaning that integral of flat matrix. And here I expect there should be some dilatonic gravity like that. So there is just some deformation of that. I expect there should be some 2D model of gravity, which is dual to Wolf-sheet, which describe Wolf-sheet dynamics.
Okay, let me go back to my technical question, which I sort of missed in some of the discussion. So this D-26 term, I understood from Ofer's talk to come from just imposing space-time Lorentz invariance. Now, what happens if your string is probing a cloud background where Lorentz invariance is broken in target? Is it still D-26 or is this term modified?
It's not a term in there. It's term in the 1PI effective action. It's not a term in the kind of action which defines the action which defines the theory. It is just calculable effect which is present there. It's one loop effect which is present there and which is related to particle production. And yeah, if you put it in, you put theory in a curved background, if it's non-dynamical background, you can definitely put gauge theory on that. One would still at least, well, it depends on the scales, but if background is curvature is long, then one expects, of course, there will be this term present. It's a large curvature background that's it's not clear well.
Okay. John?
I have a sort of naive question, which I guess is for Sergey. So in the literature on field theories on loop space by Migdal and Polyakov from the early 80s, an important role in their thinking was played by an analogy with chiral models in 2 dimensions. And in particular, the equation that they actually study is this loop equation, which they think of as like the analog of some integrability equation in the chiral sigma model. And that's, so you'll notice that didn't appear in my talk. We were studying some equations of motion instead. So my question is just whether this integrability that they were looking for, is it the same integrability that you see on the world sheet?
Yeah, I don't know. Yeah, I should look in the literature.
Maybe I shouldn't put you on the spot. And does somebody else know anything about this?
Yeah, maybe I can comment then. So I think it's different. Yeah, because like the integrability Sergey is talking about is the worldsheet integrability, whereas like integrability they're talking about is like defined in a more like abstract space, which is more like a target space. Well, not really target space, but as far as, yeah, I also try to understand the relation, but I think it's different.
Thanks. By the way, let me advertise a beautiful talk that Shota gave at the London Integrability Journal Club, where he gave an introduction to that type of integrability of loop space and so on. So you can I really recommend. I think we should test the screen share. So while we test the screen share, people are free to ask some more informal questions if she and Mukund still want to ask some more questions. Otherwise, let's thank Igor and Sergey for a nice discussion and reconvene at 40 past the hour.